We spent some time over the last few days talking about radioactivity, this natural, spontaneous, random process where a nucleus decays. The four types of radioactivity that we talked about were alpha decay, beta negative decay, beta positive decay, and gamma decay. All of these types of radiation are what we call ionizing radiation. They have the ability to ionize atoms, to turn atoms into ions. And they're all caused by some type of nuclear decay, all caused by some sort of instability in the nucleus. There are something like 2,500 different something like 2,500 different isotopes of nuclei, and something like 90% of those different isotopes are radioactive, producing one or more of these types of radiation. Now, each of these types of radiation can be produced by any one of a number of different radioactive nuclei, but not necessarily at the same rate. We spent yesterday talking about the rate at which these decays occur, and we defined a new term called the half-life. The half-life of an element was the time that it takes statistically for half of a radioactive sample to decay. Why do we add that word statistically in there? Why don't we just say it's the time that it takes for 10 kilograms to become 5 kilograms? Philip? It is a bit variable, right? It's based on probability. And if we have a big enough sample size, the statistics usually work out pretty well. The laws of probability dictate that if you flip a coin 10,000 times, you're going to end up pretty much with 50% heads and 50% tails. But not for sure, not 100% for sure. We say statistically because on average, that's the way it's going to work out to be, but we don't really know exactly how it's going to work out to be until after it's already happened. The half-life is the time statistically that it takes for half of a radioactive sample to decay. Now remember that when it decays, it's not decaying into nothing. It's not like 5 kilograms becomes 2.5 kilograms. It's 5 kilograms of something becomes 2.5 kilograms of something else, and 2.5 of it is still what it was. You still have 5 kilograms. It's just half of it has decayed into something else. We also talked about transmutation. Transmutation is the conversion of one element to the other to another that can happen, among other ways, by radioactivity. We're going to learn 2 more ways later today about how transmutation can occur, how one element can change into another element. Let's go back to half-life for a second, though. We define the half-life as the time that it takes statistically for half of the sample to decay. We're going to say the number of half-lives, n, is equal to the time divided by the half-life. So if the half-life is 5 years and you have 15 years gone by, then that means the number of half-lives would be 3. We have another equation as well that we learned yesterday that a lot of you recognized from math class. N is equal to n0 1/2 to the little n. Little n, of course, the number of half-lives. N0 would be the initial amount, and the initial amount can be measured in just about whatever you want, as long as it indicates an amount. It can be kilograms or grams; those would be the common ones, right? It can be a number of nuclei. It can be a percent. If it's a percent, by the way, what's n almost always going to be? Sorry, what's n0 almost always going to be? 100%, usually, right? It could be becquerel. We saw that unit yesterday, though I told you not to panic about what that means. Okay, it's a decay per second. But the bottom line is, if you have anything that indicates an amount, a rate of decay, a number, a mass, or a percentage, or anything like that, then it's either going to be big N or N0. N0 being the initial amount, and N being the final amount, the amount that you end up with. Now, these are the only 2 equations you're going to use. It does get a little bit tricky sometimes because it looks like we have to use logarithms sometimes. And question number 10, as we go over it from our worksheet, that's one of those questions where I'll demonstrate how you can use logarithms or what the alternative to using logarithms are for those of you who are not comfortable with using logs. Let's go over our worksheet now. We had requested 3, 4, 5, 6, 7, and 10. So let's go over that now, starting with question number 3. So the original activity of polonium-210 is 100 becquerel, 100 decays per second. What's the activity after 2 years if the half-life of polonium-210 is 138 days? We're going to say T1/2 is 138. We're going to say 2 years have gone by. The time is 2.0 years. Now we want to convert one of these to make sure the units are consistent here. Days, years, I don't care, but make sure they're consistent. What do you want to do? Convert days to years or years to days? Years to days? Okay, so if we multiply that by 365, we're going to end up with 730 days. Now, somebody this morning said, in fact, a couple people this morning said, one in each class, said, do we multiply it by 365 or 365 and a quarter? Because really, there's 365 and a quarter days, or I mean, days in a year, right? Multiply it by 365. Odds are you're not going to have to do that conversion on a test because they're not going to want to trick you with that. But if you do, go with 365, not 365 and a quarter. Got it? I doubt you'll have to do it, but if you do, go with 365, unless they say otherwise. All right, so there's the time and there's the half-life. What else have we got here? We've got something is equal to 100 becquerel. Tell me what variable that is. That's going to be NO, N0, the original amount. And we're looking for the final amount. We're looking for the value of N. So we're going to say N is equal to N0, 1/2 to the little n, but we don't know what little n is, so let's find that by saying T over T 1/2. Let's say it's 730 days divided by 138 days. We have a time here of, let's see, 730 divided by 138 gives us 5.2899. Okay, there's the number of half-lives. Now, when we solve this, when we get N, would we expect N to be bigger or smaller than N0? Smaller. 5 half-lives have gone by. With each half-life, you're going to cut what you have in half. So we're going to be quite a bit smaller than the original amount here, right? Start with 100 becquerel, 1/2 to the little n, 5.2899. Let's figure that out on our calculator together now. We'll say 100 times 0.5 to the 5.2899. Gives us a value of 2.56. All right, sure enough, we had 5 half-lives. We expected it to be quite a bit below the original amount. It is. It's 2.5% of the original amount. Is that okay? Who asked me for number 3? Nobody wants to volunteer that? Yes? It's okay? All right, number 4. We're going to do maybe one of them from question number 4 because they're all pretty much the same, right? Let's go 4B, I guess it is. Numbered kind of weird, but let's go the second question in number 4. The half-life of carbon-14 is 5,730 years. We see pretty varying half-lives, right? Anywhere from 10 to the minus 23 seconds to 10 to the positive 7 years. Pretty dramatic differences in the half-life. This is somewhere in between. Our time that's elapsed here is 3,000 years. Now, that's less than 1 half-life, right? Would we expect the final number to be bigger or smaller than the original number when we've gone through less than 1 half-life? It'll still be smaller. It's just not going to be that much smaller, right? It's going to be, if we start off with 100%, then our final amount is going to be somewhere between 50 and 100%. We know we're less than 100, but we know we're more than 50 because we haven't had one entire half-life elapse. We're going to do this pretty much the same way as we did the last question. We have to solve for a little n using T over T 1/2, 3,000 divided by 5,730. It's going to give us somewhere in the range of, I don't know, 0.5 or 0.6. 0.5236. And now we're going to say it's 100 times 1/2 to the 0.5236. Let's figure that one out as a group now. 100 times 0.5, 0.5236. I almost did a times 10 to the something there. Be careful not to make that mistake, okay? It's not times 10 to the 0.52. It's just 0.5 to the 0.5236. Gives us 69.6%. Actually, it should be 4 digits, shouldn't it? 69.56%. Which is bang in that range that we expected. Something below 100%, something above 50%. Pretty much right in the middle there. 5. The activity of carbon-14 is 20 becquerel. What's the original activity of 3 half-lives have elapsed? I'm going to say n is equal to n sub 0, 1/2 to the little n. We're going to say big n0 is equal to what? N over 1/2 to the little n. The amount that we start with is what we're looking for. The amount that we end with is 20 becquerel over 1/2 to the 3. We don't even need the half-life here. Okay, we're given the number of half-lives. That's always what we want out of this. 20 divided by 0.5 to the 3 gives us 160. Wait a second. Didn't we say we always go down in number? Didn't we go up here from 20 to 160? We ended up with a number that was bigger than what we started with? Well, our calculation was bigger, right? But, Mitchell, what's the deal there? Yeah. Yeah, we're trying to find the original. So when we look at this as being the original, this is the final. The final is clearly less than the original. So 160 makes sense, right? I think question number 6, pretty much the same. I'll address one little thing in question number 6, though. We're going to set it up the same way. N0 is equal to n over 1/2 to the little n. You just got to find little n here. And little n, of course, is going to be equal to t over t 1/2. It's 2,000 years divided by what? Just check a previous question. Right? Just check one of the other questions where it tells you the half-life is 5,730 years. So get that, get the number of half-lives, and then sub it in the same way as we did in question number 5, and you should be good to go there. The answer for that was, if you forget from when I gave you the answers, it was 127 becquerel, which seems reasonable again. If this is our original amount, our final amount is 100. We have less than 1 half-life have gone by, so seems reasonable. 7, like this question, and a bit different too. It says, find the ratio of the current activity to the original activity of carbon-14 after 11,460 years have elapsed if the half-life of carbon-14 is 5,730 years. The ratio. Everybody open up your imaginary physics thesaurus again. What's another word that means the same thing as ratio? Same thing as compare, ratio, compare, divide. Good. Divide is our word here, right? We want to find this ratio we divide. It hasn't been very long since we found another ratio where we divided. That was the charge to mass ratio. You remember when we were finding the charge to mass ratio, we set FC equal to FM. We said mv squared over r equals qvb. Did a little canceling there, and we end up with q over m is equal to v over b times r. If we knew when we did the cathode ray tube what q was and what r was, the charge to mass ratio would be easy. We just divide the charge by the mass. But if we didn't know what charge was and we didn't know what mass was, then we could divide v over b times r to also get the charge to mass ratio. We're going to do something similar here. We don't know what n is and n0 is. That's what we want to find, right? So let's derive an expression to get me n over n0. We know our base equation is n is equal to n sub 0 1/2 to the little n. Let's divide by n0. So just like we didn't know what q was, we didn't know what m was, we had to find the charge to mass ratio by using other variables. Here we don't know what n or n0 is, we have to find the charge to mass ratio by using other variables. So let's get little n and then set it as the exponent and find out what 1/2 to the n is, which of course corresponds to the ratio of n to n0. Little n is going to be, what, 11,460 years divided by The half-life, which is 5,730 years, gives me 2. So we're going to say n over n0, that's the ratio of n to n0 is equal to 1/2 to the 2, which I believe ends up being 0.25. So we could say my ratio is 0.25, or you could say it's 0.25 to 1. Either one of those ways of expressing it would be correct. This is a multiple choice question. You just kind of got to go with the way they express it, right? 0.25, 0.25 to 1, however they write it. Yep. Yeah, absolutely. Yeah, absolutely. In fact, if you see this on an exam, that's probably what they do is say it's a 1 to 4 ratio as opposed to a 0.25 to 1 ratio. Same thing, right? It's pretty easy to express as whole numbers, right? 1 to 4. Sometimes, though, this number is so weird that it's pretty hard to express like that. But absolutely. I mean, you could express it as a 25 to 100 or a 4 to 16 ratio if you wanted. That would be the more common one, obviously, though. All right, good. Finally, question number 10. Number 10 says, how many half-lives would it take for a radioactive sample to decay to 25% of its original value? So we're going to say, what my original value is going to be 100%. My final amount will be 25%. We know the half-life of carbon-14. No, it's not carbon-14. Doesn't tell me. So we don't know the half-life. We just want to find little n. That's all we got. Why is it 25? No, we keep it as 25. The question, if you didn't hear that, was why wouldn't we subtract that from 100 and say the final amount is 75%? Because that's not the final amount. If we start with 100%, we're not saying how many lives would it take to decay by 25%. It's decay to 25%. So this is what it is now. If it was 100 grams, now it's 25 grams. So that's not how much it's gone down by, it's how much it is at the end. Okay, so here's what we want to do for this. N is equal to n0, 1/2 to the little n, but mathematically that becomes kind of icky. If we want to solve it mathematically, we've got to use logarithms. But remember, I told you, you're never going to actually have to use logarithms. Let me go through that process just in case you want to use logarithms. This is going to be log of what? N over n sub 0, 25 over 100, divided by log 1/2 or log 0.5. Let's divide that by log 0.5. Get 2. There's my number of half-lives. But listen, if you don't like doing it that way, if you don't remember even doing logarithms in math class, or you didn't like it when you did it, then we use the divide by 2 method. The divide by 2 method says just set up a little table. N and N, little n and big N. After 0 half-lives, I've got 100%. After 1 half-life, I've got 50%. And after 2 half-lives, I've got 25%. So how many half-lives have gone by? 2. The divide by 2 method, of course, only works if it's a whole number of half-lives, which it will be in this context for you, because as I mentioned yesterday, our curriculum tells us we only have to perform non-logarithmic half-life calculations. Doesn't mean you can't use logs, just means that there's always got to be another way. Some people took physics 30 in semester 1 and had never done logarithms, so we wouldn't expect them to be able to use logs. All right, have a look at the bottom of the example question sheet that I gave you yesterday. You're going to see a graph, the same graph that you see up on the board right now. This graph is what we call a radioactive decay curve. And every time we see a radioactive decay curve, it's going to have the same shape. Numbers will be different. The variables on the axes may be different. The x-axis will always be time. The y-axis will always be some form of n, but that could be kilograms, it could be percent, it could be counts per minute. It's the amount versus time. You will always see that graph taking this shape, a curved line curving downwards. That means that we cannot analyze it using the equation y equals mx plus b. Now, we have seen a couple of times that you're able to straighten a graph. For instance, if you had EK versus speed, it would curve upwards like this. If we plotted EK versus V squared, right, EK is equal to 1/2 mv squared, we would get a straight line and we'd be able to analyze it. We're not going to try to straighten this one out. Okay, this would not be pretty if we try to straighten this one out. So we're going to leave it just like this. And that's okay, because most of what you would need to get out of this, all of what we need to get out of this, can be read directly on the graph by doing one of two things. You will either go over and down on the graph, over and down, or you will go up and over. You won't ever do anything else besides over and down or up and over. What are you going to be asked to solve for in one of these graphs? And this graph, by the way, will not be that graphing question that I keep telling you about, right? They're going to expect us to do more than up and over on that graphing question that I keep telling you guys about. Well, one of the things that could be asked is, how much time does it take for 80 counts per minute to decay to, let's say, 20 counts per minute? How much time does that take? What are we going to do for that? Let's go over and down. Let's go down to 20, go over. Oh, look, it takes 4 days to go down to 20 counts per minute. If I want to find out how long it takes to go to 10 counts per minute, I would go over and down, and it looks to be about 6 days. What if I asked you for the half-life? What is the half-life of this radioactive material? Remember, I told you it's either up and over or over and down. What's the half-life? Devin? How do you know it's 2 days? Good, exactly. If we start at 80, after one half-life, you're down to, statistically, you're down to 40, right? So we're going to go over to 40, over and down, and it looks to be 2 days. The half-life of this would be 2 days. Make sense? What if I asked you how much remains after 6 days? Go up and over. 6 days, up and over. Oh, looks like 10 counts per minute remains after 6 days. How much remains after 1 day? Up and over. Looks to be about 54-ish counts per minute. This is a question on a test, by the way. You're going to have a lot more grid lines to be able to distinguish exactly what the number is. Let's do one question together. It's question number 12 on the worksheet that we just finished going over. I won't ask you to do that yourself. We'll just take a look at it as a group here. It says we got a radioactive decay curve. We've got the number of radioactive nuclei on the y-axis, that's n, and we got time in days on the x-axis. Looks like the same graph, same shape. First question says, what's the half-life of element X? Diamond, how do I get the half-life of element X? I ask you because I know you know the answer. Yeah, from 30, exactly. We start off with 60, we get down to 30, which is what we statistically have left after one half-life, over and down, and it looks to be about 1. It's pretty hard to tell on this graph because of the way that I have it drawn, but it looks to be about 1 day. How much of element X remains after 2 days? Well, let's go up and over from 2 days. Looks to be about 15. About 15 nuclei. C, how much element X remains after 3 half-lives? Well, if the half-life was 1 day, then 3 half-lives is 3 days. So we'd go 3 days here. Up and over, looks to be, I don't know, about 8. Roughly 8 remains after 3 half-lives. 7.5 or so. How long does it take for element X to decay from its original amount to 10 nuclei remaining? Let's go over and down. 10 over and down. Looks to be about, I don't know, about 2.5-ish. give or take a little bit. Again, on a test, it would be a little bit easier to determine because the graph would be a bit better. Man, we hope we get a question like this, right? Because it's up and over, over and down. It's like if you can't figure out what to do, like guess one and see what happens. If it doesn't work out for you, then do the other one. It's got to work out. 50-50 chance, right, of guessing correct the first time. I know for sure you're going to get one of these questions on your unit assignment. It's going to be posted here in another hour or so. You're also going to get one on your unit test next week. And odds are you're going to get one on your diploma exam as well, which is good because they're easy. All you have to do is up and over, over and down.